show to you is simply find a way, okay, to produce tan theta in this expression here, okay. So how do we produce tan theta here? We can actually produce tan theta here. We can produce tan theta here. How? If we divide each term on the top and on the bottom by cos, we are going to produce tan. This is what I'm talking about here. If I want to do that here, it becomes 2 sine. Let's divide top and bottom by cos. So it becomes 2 sine divided by cos. Then here we have 3 cos divided by cos. Okay, divided by, we have 4 cos theta divided by cos theta. And we also have here 3 sine theta divided by cos theta. Okay, now at this point in time, you can cancel out here. You can also cancel out here. Okay, now also something you see clearly is, remember that sine theta over cos theta is tan. So we can have here, we have 2 tan theta plus 3 divided by 4 plus 3 tan theta. Okay, this is what we have here. So all we need to do is just to replace, tan theta is 4 over 3. Let's replace it here. If we replace, we're going to be having this 2 into 4 over 3, 4 divided by 3, okay, plus 3 divided by 4 plus 3 into 4 over 3. So what we have here, we have 8 divided by 3, 8 divided by 3, okay, plus 3. Here we have 4 plus 12 over 3, okay. So at this point in time, if we get the XCM, the LCM here, we're going to be having, we get the LCM here, we're going to be having, on top, we're going to be having 3, then 3 into 3, 8. So we have 8 plus 8 plus 9, okay, 8 plus 9. We have 8 plus 9 here, divided by 12, 12 plus 12 divided by 3. So what we're going to be having here, finally, we're having 17 divided by 3. Okay, we're going to have 17 divided by 3, okay, divided by 24 over 3. So what this gives us becomes 17 divided by 3 times 3 over 24. These two can go out. So we're going to be having 17 over 24 as the final answer, okay? All right, remember I talked about flexibility, okay? I talked about solving this question with 2 different methods, okay? Now, the other method that is possible here, okay, is to do something like this. Draw a triangle, okay? Draw a triangle. This is the angle, and tan is, remember, tan is opposite over adjacent. So what we have here becomes opposite over adjacent, okay? So we have to look for the remaining side. The remaining side here should be using Pythagoras, can be gotten using Pythagoras rule. And that gives us 4 squared plus 3 squared. This gives us square root of 25, and that would be 5. Okay. So what we have here on this long side is 5, 4, and 3. Normally Pythagorean triple should tell you here's 4 and here is 3. The remaining side should be 5. Okay. So that will make you actually very fast. Now, if I know this, then I can get sine. Sine is actually opposite over hypotenuse. So opposite is 4, hypotenuse is 5. Then I can get for cos theta 2. Cos theta should be adjacent over, okay, hypotenuse. Alright, that's car. Okay, so if I have this, I can easily just replace what I have. I can replace sine and cos here. So this gives me 2 where I see sine. I'll be having 4 over 5. Okay, plus where I see cos. Where I see cos, I'll be having 3 over 5. Okay, divided by, here we have 4 into where I see cos again. I'll be having 3 over 5 there. And where I see um, sine again, I'm going to be having 4 over 5. Okay. So in this case, now if I multiply 2 times 4 is 8 divided by 5 plus 9 over 5 divided by 12 over 5 plus um, 12 over 5 here plus 12 over 5 again. So what we have here becomes we have 17 over 5 divided by 24 over 5. Okay, so this gives us this gives us 17 over 5 times 5 over 24. You know, normally divided, if you change to times, it's going to swap the denominator goes up. Okay, so 5 can go up. So 5 and 5 can cancel. So we have 17 divided by 24. You can see that the answer we got here with the first method is 17 over 24. And the answer we're having here is still 17 over 24. So whichever method you prefer, you can use it. Okay. Okay. This question here says that we should show that this guy is equal to this guy. Okay. Now, how do we go about this? It is still a very simple technique. Okay. So I want to see how I can, using trigonometric identities, prove that the left hand side is equal to the right hand side. Okay. Now, so what we have here is actually tan theta over sec theta minus 1 being added to tan theta over sec theta plus 1. Okay. Now, if I look, okay, I can decide to look for the LCM. But before doing that, I can see that tan is common here. So I can easily factorize tan theta outside. So when I factorize tan theta, I'll be left with 1 over sec theta. I'll be left with 1 over sec theta minus 1 plus 1 over sec theta plus 1. This is what I have now. So at this point in time, I can look for the LCM. Okay. Now, if I look for the LCM, I am going to have the product of this guy and this guy. Okay, that is sec theta minus 1 multiplied by sec theta plus 1. I'm going to have this here. Then sec theta going to this, will have sec theta plus 1 multiplied by 1. We'll be left with sec theta plus 1. Okay. Now again, sec theta plus 1 goes into what we have here. We'll be left with sec theta minus 1 multiplied by 1. Remember, there's addition here, so it becomes addition. We'll be left with sec theta minus 1. Okay, what we have here. So again, we can now say from here that tan theta, remember that the bottom is actually the product of two conjugates. Okay, that gives us difference of two squares. So we're having what we have here becomes sec squared theta minus 1. Okay, then we have positive 1 and negative 1. We actually go out. So we're going to be left with 2 sec theta at the top. Now you have to recall that from trigonometric identities, remember that 1 plus tan squared theta gives us sec squared theta. Okay? So it means that if I should make tan squared theta the subject, it gives us sec squared theta minus 1. Alright? So it means that where I see sec squared theta minus 1, I can replace with tan squared theta. So I can have tan theta into 2 sec theta divided by tan squared theta. Okay. Now at this point, one tan will go out, we kill out one tan. Okay. Then we'll be left with 2 sec theta divided by tan theta. Now you can see that we're very, very close to our answer. This is the same thing as saying something like this. Uh, Sec theta is inverse of cos. So it becomes 1 over cos theta. Then we have tan here. Tan is sine over cos. So it's like saying divided by sine theta divided by cos theta. Okay. So at this point, we can still do this. We could say this gives us 2 times 1 over cos theta. If I change this to times, you know that cos goes up and sine comes down. So we have cos theta divided by sine theta. Now cos can cancel out cos. Okay. So we are left with 2 over sine. 2 divided by sine gives us 2 cosec theta. Okay, so you can see that we have been able to, from our deduction, show that the left hand side is equal to the right hand side. All right. Mm. Now wait. Question here says that we should, given that if a squared, a cos squared theta plus b sin squared theta is equal to c, it says that we should show that tan squared theta is this guy. Okay. So what I'm going to do from here, I'm going to remember that from a cos squared theta plus b sin squared theta equals c, I would recall that sine squared theta is equal to 1 minus cos squared theta. This is a trigonometric identity, okay? Now, so it means where I see sine squared theta, I can substitute with this guy here. So, replacing, I have a cos squared theta plus b into 1 minus sine squared theta. Okay, 1 minus, I'm placing 1 minus cos squared theta here, so it becomes 1 minus cos squared theta here, okay, is equal to c. So I'm going to have a cos squared theta plus b times 1, b times this guy becomes b cos squared theta equals c. So if I carry b to cross, I'll be having a cos squared theta minus b cos squared theta, which is actually equal to c minus b because I move b over to the other side. Okay, so what I have here, I have that cos squared theta is common here. So if I bring out cos squared theta here, I'll be left with a here, and I'll be left with b here. Okay, this is equal to c minus b. Okay, so if I make cos squared theta subject, if I make cos squared theta subject, I'll be having that cos squared theta is going to be c minus b divided by this guy here, a minus b. Okay, so I'll remember also that there's a trig rule that I have to recall at this point. I will recall that 1 plus tan squared theta is equal to sec squared theta. Okay, so it means that tan squared theta is going to be equal to sec squared theta minus 1. Now, how do I obtain sec squared from cos squared? The inverse of cos is sec. So the inverse of cos squared is going to be what now? Sec squared. So it means that sec squared theta would be the inverse of this. That will be a minus b over c minus b. So it's going to be a minus b over c minus b. How did I do this? Remember that 1 over cos squared theta gives us sec squared theta. Okay. So at this point, if I substitute sec squared theta here, I'll be having that tan squared theta is equal to a minus b over c minus b minus 1. All right. So at that point in time, I'll just look for the LCM. Okay. I'll just look for the LCM there. So I'll have that tan squared theta becomes equal to LCM is c minus b. Okay. LCM is c minus b. So c minus b into c minus b gives us 1. 1 times a minus b gives us a minus b. Okay. 1 into c minus b is c minus b times 1 gives us negative 1 into c minus b. So we have a minus b minus c plus b divided by c minus b. Now, minus b goes out with b. Okay, so we have what we have left here becomes tan squared theta is equal to a minus c over c minus b. Okay, well, remember Remember that the question says we should show that tan squared theta is equal to c minus a over b minus c. That's what the question said. We don't say that. So the question said we should show that is equal to c minus a over b minus c. So if I factorize negative sign from both top and bottom, this is what I stand to have. So if I bring out negative sign from here, I'll be having negative into c minus a. If I bring a negative from, I'll have negative into b minus c. So these two guys can go out. Okay. Now when these two guys goes out, finally we have determined our proof. This gives us c minus a over b minus c. Okay, so this is the correct answer. Okay, that what we have here is equal to this guy. Okay, now I can easily recall this. Remember that cos squared theta is equal to 1 minus sine squared theta. Okay, and also recall that from difference of two squares, remember that 1 squared minus sine squared theta is the same as 1 plus sine theta into 1 minus sine theta. Okay, that's an algebraic identity. Okay, now we can actually say from here that replacing with what I have here, I can have that 1 plus sine squared theta. Okay, so 1 plus sine theta all squared. If I place this guy here, I'll be having 1 plus sine theta into 1 minus sine theta. Okay, now I would see clearly that 1 plus sine theta is common because it is here, it is also here. So if I factorize 1 plus sine theta from here, I'll be left with 1 plus sine theta here, and I'll be left with 1 minus sine theta here. Okay, now minus sine and plus sine, minus sine and plus sine are going to go out. So what we have left, 1 plus 1 is 2. So what we have left is what? 2 into 1 plus center. So I've been able to show that the left hand side here is equal to the right hand side. All right, what we have here is to show that the left hand side is equal to the right hand side. Okay, now I can see clearly from here. We can apply difference of two squares here. How do we go about that? Remember that when I have a minus b multiplied by a plus b, the result is a squared minus b squared. Okay, so if I apply same thing here, the result becomes cosec squared x minus cot squared x. Okay, so if this gives us this. Okay, and also remember that we said that 1 plus cot squared x is equal to cosec squared x. Remember this. Okay, this is an identity. This is a trigonometric identity. Now, one thing you should observe here is that in our deductions, we normally apply the trig identities. Now, this is a trig identity that 1 plus cot squared theta gives us cosec squared theta. So I can substitute cosec squared as 1 plus cot squared. So we have 1 plus cot squared x minus cot squared x. Okay, this gives us 1. Okay, so I'm able to show quickly that everything here is equal to 1. All right. This is another question here that says that we should show that what we have here is equal to 2. All right. So quickly, I need to be able to expand this and this. Okay, I need to be able to expand it. So if I expand x plus y squared is same as x plus y multiplied by x plus y. Okay, and this is same thing as saying x squared plus yx plus xy plus y squared. All right. So this gives us x squared plus 2yx plus y squared. Okay, this is what it gives to us here. Now, then if we let's do the same thing for expanding x minus y squared. Okay, this gives us x minus y into x minus y. This gives us x squared minus xy minus yx plus y squared. So this gives us x squared minus 2xy plus y squared. Now, so if I expand this properly, I'm going to get this. If I expand this properly, I'm going to obtain this. Okay. Now, in the same way, if we apply the same concept here and expand this guy here, I'll be having that sine theta plus cos theta. If I square this, is going to give me sine square theta plus 2 sine theta cos theta plus cos squared theta. Okay, this is what it gives to me. In the same way, if I expand this guy here, I'm going to have sine theta minus cos theta all squared. It gives me sine squared theta. Okay, then minus 2 sine theta cos theta. Okay, then plus cos squared theta. All right. Now remember, we are adding this guy to this guy. So we are adding these two. If we add these two, remember that these two guys will go out. Okay. Now if I add this plus this, I'm going to be having 2 sine squared theta. If I add this plus this, I'm going to be having plus 2 cos squared theta. Now see that 2 is common, so bring it out. If we bring 2 out, we're going to be having 2 into sine squared theta plus cos squared theta. Now remember that from trig identity, the addition of sine squared theta to cos squared theta gives us 1. So this is same thing as saying 2 into 1, and that gives us 2. Alright, so I've been able to show that what I have here is equal to 2.